Okay, very good morning, my dear students. So in the last class, we have started phase shift keying. In the last class, we have started phase shift keying section. Okay. So in this module, already I told you that we'll discuss the performance of PSK transmitter and receiver sections. Okay. And let us go through the, we have already discussed the general equation for phase shift keying. What is the general expression for phase shift keying? AC cos omega CT plus phi. Okay, what is the general equation for phase shift keying? AC cos omega CT plus phi, where phi is the phase variations. Okay, where phi is the number of phase variations. It depend on the number of bits transmitted. Okay, number of bits transmitted per symbol. For example, if we transmit n number of bits per symbol, we will have n number of phase variations. But here in the case of binary phase shift keying, which is a simple form of ASK, we will have only one bit transmitted per symbol. Okay, so we will have only one like two phase variations, because m is equal to 2 power n. So if we have n number of bits transmitted per symbol, the number of phase variations will be 2 power n. For example, if n is equal to 1, then we will have m, that is 2 power 1. So 2 variations will be there. So if we want to divide the total 360 degree into 2 angles, we can state as no phase variation and phase variation. So no phase variation is for 0 or 360 degree and phase variation is 180 degrees. Okay, so this is the general equation for PSK. What is the general expression for PSK? AC cos omega CT plus phi, where phi is the phase variation that depends on the number of bits transmitted per symbol, and the phase variation, number of phase variations is equal to m, where m is equal to 2 power n. Okay, so already we stated the general equation for binary phase shift keying. It will have two phase variations. One is at 0 degree and other is at 180 degrees. One is at 0 degree and other is at 180 degrees. Okay, so whenever the data bit is 1, whenever the input is 1, we will have no phase variation. That is, the phase variation is 0 degree or 360 degree. Okay, but whenever the phase variation is 180 degree, that occurs for the data bit 0. Okay, please substitute the value of 180 degree in the general equation. What is the general expression? AC cos omega CT. Okay, plus phi. Already we discussed that phi value is 0 when x of t is 1. So when x of t is equal to 1, replace phi value as 0. So you will get directly AC cos omega CT. Okay, so whenever x of t is 0, so it will be AC cos omega CT plus 180. It will be minus AC cos omega CT. See, already we discussed all these general expressions of BPSK and everything in the last class. Just I am recollecting all the points for you. Okay, so what is the general expression for BPSK? It is plus AC cos omega CT when input is equal to 1, and when input is equal to 0, it is minus AC cos omega CT. So here we can represent the above equation of BPSK signal by using the bipolar energet signal, where B of t is the bipolar energet signal, which you can define it as either plus 1 or minus 1. You can define it as either plus 1 or minus 1. So B of t is plus 1 for x of t 1, and when input x of t is 0, B of t is equal to minus 1. Okay, so what is the general expression for BPSK signal? B of t into AC cos omega CT, where B of t is plus or minus 1. That's why we can write it as plus or minus AC cos omega CT. It is plus cos AC cos omega CT when input x of t is equal to 1. It is minus AC cos omega CT when x of t is 0. So general expression is in terms of bipolar energet, that is B of t into AC cos omega CT. Please remember this equation of BPSK, so that we can use the generation technique. Already we discussed that coming to the generation, B of t into AC cos omega ct is our BPSK signal. Okay, so first you should generate the bipolar energet. See, already I told you in the last class that unipolar energet should be converted into bipolar energet in order to get BPSK signal. So you need a level shifter. You need a level shifter. So level shifter or level encoder is used for conversion of unipolar energet to bipolar energet. But in the case of ASK, we will directly apply the unipolar energet to the multiplier. But here unipolar is converted into bipolar and that is multiplied with the carrier component. So that our BPSK signal is B of t into AC cos omega ct or plus or minus AC cos omega ct. This, see, you can observe the the generation of BPSK signal is very simple, but the complexity arises in the coherent detection. So the circuit of detection of BPSK signal is very complex. You can see it in the today's session. Okay, so you can replace AC as root 2 PS. This is all to get the Euclidean distance. This is all to represent the expression in terms of 1 bit energy carrier, So BPSK signal is equal to B of t into AC cos omega ct. So you can write it as B of t into root 2 PS into cos omega ct. So that's why we can also rewrite the expression for BPSK signal as plus or minus root 2 PS into cos omega ct. Okay, now let us represent the expression in terms of 1 bit energy carrier. Okay, let us represent it in 1 bit energy carrier. To represent in 1 bit energy carrier, you should represent in terms of symbol energy. So the product of PS and TS gives you the ES, that is symbol energy. So upon replacing the expression, you can divide in numerator and the denominator with respect to TS, or else you multiply directly. Multiply the numerator and denominator with root TS, so that you can get B of t into root PS into TS into phi 1 of t. What is root PS into TS? Root ES, because the symbol energy is defined as the product of power dissipated per symbol and symbol duration. So just we replaced root PS into TS as root ES. But what is B of t? It is bipolar energet, which is equals to plus or minus 1, Okay, so you can observe here that you can finally obtain the BPSK signal as plus or minus root ES into phi 1 of t. So it is plus root ES into phi 1 of t for x of t 1, and it is minus root ES into phi 1 of t for x of t 0. Now how can you get the Euclidean distance? You can evaluate the Euclidean distance. By taking the difference between the magnitude of energies for 1 bit energy carrier at the locations 1 and 0. So at 1 we will have the magnitude as root ES, and at 0 you will have the magnitude of minus root ES. So taking the difference between those two, we can get the Euclidean distance as twice to the of ASK signal or amplitude shift keying signal. So that's why, so what is the Euclidean distance of BPSK compared to ASK? Here it is 2 into root PS into TS, that is twice that of ASK, because in ASK the Euclidean distance is root PS into TS. So we can say that the Euclidean distance is twice to the of, that is you are increasing the Euclidean distance in ASK signal. So already I told you that as the Euclidean distance increases, the probability of error will reduce. So what is the advantage of BPSK? The probability of error is less. Okay. So next point is, here BPSK is less susceptible to noise, because in the case of BPSK, the signal don't undergo any amplitude variations. It doesn't undergo any amplitude variations because the amplitude of PSK signal is constant. Not only the amplitude, frequency is also constant. Okay. So up to this we studied in the last class. Okay, even we calculated the bandwidth. So here the generation principle behind BASK and BPSK is same, because we will directly use the multiplier. But the multiplier inputs are unipolar energized and carrier in the case of ASK. But in the case of PSK, what are the two components? It is equals to one is bipolar energized and other input is as usual the sinusoidal carrier. So bipolar energized is B of t, which is plus or minus 1, but unipolar is magnitude is 1 for high level and 0 for low level. Okay. So what is the bandwidth? It is the difference between the upper cutoff and lower cutoff. Once the signal, the carrier component is multiplied with the bipolar energized, our cutoffs will change from FC towards plus or minus FB. So that upper cutoff will be FC plus FB and lower cutoff will be FC minus FB. Okay. So that's why difference between those two is twice that of FB. So here you can observe that in terms of bandwidth, both BPSK signal and BSK signal resembles the same. Okay, so same bandwidth is maintained for both the signals. Okay, let us go through the next slide. So here you can start with the BPSK demodulation. BPSK demodulation. Now here if you observe the demodulation, here we will have coherent detection. Okay, so the coherent, here we will have only the coherent detection. Here we will have only the coherent detection, and using the transmission technique, using the general transmission technique, it is like the multiplier at the transmitter. It is very difficult to use the non-coherent version at the receiver. So in BPSK we will have only coherent detection, but the non-coherent version of BPSK, that is both the transmitter as well as receiver, will change. The transmitter section and receiver section of DPSK is completely different to that of BPSK. So the non-coherent version of BPSK is differential PSK, where the transmitter section will also change. So in the transmitter we don't have multiplier. So we will have different technique in the transmitter as well as the receiver. That is the non-coherent version of BPSK. There also we will generate the same BPSK signal, but the transmitter and the receiver sections is completely different. Okay, let us go through the coherent detection. So let us see the coherent detection using the synchronous carrier, and the transmitter section is what we discussed in the earlier class. That is the multiplier whose inputs are the B of t and the carrier. Okay, let us go through coherent detection. And non-coherent version of BPSK is differential PSK. Let us go through the synchronous modulation. Now please observe the coherent detection of BPSK signal. If you observe the circuit, please observe the circuit of coherent detection. Please observe the coherent detection, circuit of coherent detection of BPSK signal. What is the input to the BPSK what is the input to the receiver sections? What is the input to receiver section? What is the input to the receiver section? That is the modulated signal. That is modulated signal. What is the general form of BPSK modulated signal? We discussed. What we discussed? B of t into AC into cos omega ct. That's all. But here the input for the receiver we took as omega ct plus theta. What is the theta? Theta is the introduced phase deviation. What is theta? Theta is the introduced phase variation due to noisy elements in the channel. Due to noisy elements in the channel, let the phase variation created by the noise present in the channel be theta. What is theta? Theta is the noise present in the channel. That noise creates the phase variation. So let that phase variation be theta. That is mainly due to the noise present in the channel. Okay. So what is the general form of BPSK signal? B of t into AC cos omega ct. But here we are introducing a phase variation of theta due to the noise present in the channel. Now that's why we have modified the signal as B of t into AC cos omega ct plus theta is added here. That's all. Other than that, everything is same as that of the general BPSK signal. So the input to the receiver is noisy band limited PSK. So because of that noise component, we are introducing the phase variation as theta. Now this detection uses synchronous carrier, because already we discussed that in the coherent detection we will have synchronous carrier. Synchronous carrier. Now how can we generate the synchronous carrier? Actually, here we need to generate the synchronous carrier by using the BPA received signal. But in the case of the earlier the ASK we discussed, there what we discussed, we considered the phase variation as cos omega ct, okay, and direct and without any phase deviation, because in ASK the phase is constant, the amplitude will only change. So that's why in that case we did not introduce any phase variation, because cos omega ct plus theta, directly we took the same expression and multiplied it with BASK signal. But in the case of BPSK, this signal using this component, that is phase variation theta, we should generate the coherent carrier. We should generate the synchronous carrier. Now let us see how many steps are needed to generate the coherent carrier. What is coherent carrier? The carrier having same frequency and same phase as that of the transmitter section. But what we are assuming? We are assuming because of theta, because of noise present in the channel, let the phase deviation be theta. So with that phase deviation theta, let us detect our message signal by overcoming that phase variation. Okay. So this coherent detection, using this coherent detection technique, we will make use of synchronous carrier. We will make use of synchronous carrier to detect the digital signal or the input message signal from the BPSK signal system, from the BPSK. Now, so how many steps are needed to generate the square coherent carrier? 3 steps. What are the 3 steps? Square law device, band pass filter and frequency divider. So how many steps are needed? One is square law device, second one is band pass filter, and third one is frequency divider. So now we can discuss the analysis in the next slide. So what this square law device will do? It just squares the angular part of the received signal, angular part of received signal. It don't consider the amplitude part, because in PSK the amplitude is constant. The amplitude of PSK signal is constant. So that's why the square law device, for the generation of synchronous carrier, this square law device did not consider any amplitude. So it do not consider B of t into AC. It considers only the angular part. What is the angular part? Omega ct plus theta. What is the angular part? Omega ct plus theta. Okay. Now this square law device, what it will do? It will take only the angular part and it will square the angular part. Okay, and that is applied to the band pass filter, and that is applied to the band pass filter. Band pass filter selects only the restricted range of frequencies and that is applied to the frequency divider. So during the analysis you can see how you can generate this cos omega ct plus theta by using the three elements. Please remember the three elements, namely square law device, band pass filter and frequency divider used for generation of coherent carrier. Now as usual the coherent carrier and BPSK signal are multiplied. That is, both are applied to the synchronous demodulator. This synchronous demodulator is nothing but the multiplier section which takes the product of BPSK signal and carrier component. What is the carrier obtained, synchronous carrier obtained from square law device, band pass filter and frequency divider? Cos omega ct plus theta. Now this BPSK signal, which is B of t into AC cos omega ct plus theta, is multiplied with the synchronous carrier, where the synchronous carrier is cos omega ct plus theta. So these two are multiplied to generate a signal. Okay, to generate the multiplier output signal. Now that output signal is fed to the bit synchronizer. Simultaneously it is fed to the bit synchronizer and integrator section Please observe the circuit. Here bit synchronizer generates the series of pulses. Okay, series of pulses, and that is applied to two switches. Please observe the series of pulse train is applied to the two switches. How can you generate the series of pulses? By using the bit synchronizer. Now the output of the multiplier, it is also applied to the integrator section. What the integrator will do? Integrator smoothens the output obtained from the multiplier. What this integrator will do? Integrator smoothens the output obtained from the multiplier. Okay. So now that is applied to the integrator section. Later, based on the switching operations of S1 and S2, integrator generates the output. We can see all these switching operations in the next upcoming slides. But just you please observe the circuit carefully and see what are the elements present in that. And circuit operation, everything we can discuss in the further slides, mathematical analysis, everything. So the output of the integrator is fed to the decision device. What is the decision device? Decision device, already I told you that it compares the output of integrator with threshold voltage. Okay, and it takes the decision as 1 when integrator output is greater than threshold. When integrator output is less than threshold, it generates the output as 0. So please observe this coherent detection carefully, because the coherent detection of BPSK, this almost the same block diagram you will use in the differentially encoded PSK. Because differentially encoded PSK, we will use the transmitter section of DPSK and the receiver section of BPSK. So that's why the same circuit you will study in differential encoded PSK. So if you are not clear here, it's very difficult to catch up at differentially encoded PSK. Because we will use the same circuit without any deviation. Same circuit is used as a receiver section of differentially encoded PSK. Because DEPSK, that is differentially encoded PSK, is a combination of DPSK transmitter and BPSK receiver. Differential PSK transmitter and binary PSK receiver. See, binary PSK receiver is a circuit what you are seeing here. So that's why you should be very much thorough with this coherent detection, because same circuit, same coherent detection technique we'll use as the receiver section of differentially encoded PSK. Okay, so please observe carefully the mathematical analysis operation of this circuit. Okay, now can we move to the next slide? Any one of the student please respond. Now, did you identify the elements present in the coherent detection? Can we move to the next slide? Please respond, any one of the student. Yes, ma'am. Okay, ma. Thank you. Thank you. Let us move to the next slide so that you can see the mathematical analysis of this circuit and the theoretical part. So already I told you that synchronous carrier should undergo phase lock with the transmitter carrier. That is, it should possess both the frequency and phase synchronization as well as the timing synchronization. Here timing synchronization is provided by the bit synchronizer. Timing synchronization is provided by bit synchronizer. And frequency or phase synchronization is provided by the coherent carrier. Is provided by coherent carrier. So how you can provide phase lock with the receiver carrier to that of transmitter carrier? The timing synchronization is provided by bit synchronizer. Okay, used at the output of multiplier. And frequency or phase synchronization is provided by coherent carrier. And you may think of theta. Theta is the introduced phase variation due to the noise present in the channel. So even because of theta, we should be able to detect the message signal properly at the receiver section. Okay, so frequency or phase synchronization can be provided by coherent carrier and timing synchronization is provided by the bit synchronizer. Okay, now how can we generate the synchronous carrier? I told you that 3 sections are used. What are the 3 sections? Square law device, band pass filter and frequency divider. Okay, so you may get a doubt. Why square law device and why to divide the frequency by 2? Actually, this frequency divider is frequency divider by 2 because this is BPSK. In MRA PSK, frequency divider should be divided by M, where M is equal to 2 power n. But here the frequency divider in binary PSK is, it is a frequency divided by 2, by the factor of 2. So what are the 3 steps used to generate coherent carrier? Square law device, band pass filter and frequency divider. Okay, so the synchronous carrier, what is the next step after generation of coherent carrier? What is the next step? The 2 signals, that is coherent carrier and the incoming BPSK, both are fed to the multiplier. Both are fed to the multiplier, followed by the low pass filter section. And the multiplier output is also applied to the bit synchronizer. Multiplier output is simultaneously applied to low pass integrator section and bit synchronizer. What is the need of bit synchronizer? It generates the pulses. It generates the series of pulses based on the multiplier output. Okay, this is used for timing synchronization. So based on the bit synchronizer output, we can be able to assess the starting and ending locations of the bit interval. And what is the what is the output of multiplier? Output of multiplier is it is also applied to the low pass filter. It is also applied to the low pass filter. We know what the low pass filter will do. Low pass filter, it will smoothens the multiplier output, or it will perform integration. Okay, so that you can get only the low frequency component. And the data based on the timing synchronization provided by the bit synchronizer, both are based on the comparison of both the data, we can generate the low pass filter output. Now that output is applied to the decision device in order to compare with the predefined threshold. What is the necessity of a decision device? To convert the signal into digital. So this decision device converts the low pass filter output into a digital signal or a binary sequence. Let us move to the next slide so that you can clearly observe the mathematical analysis of this coherent detection. Please observe the mathematical analysis. Now what is the received BPSK signal? See, this mathematical analysis is very important because same circuit we will use in the case of differentially encoded PSK receiver section. Because differentially encoded PSK, it consists of differential PSK transmitter and binary PSK receiver. Binary PSK receiver is coherent detector, same circuit. So same mathematical analysis you should do in differentially encoded PSK. So now please let us go through the each and every step. Please observe carefully. What is the received BPSK signal? BPSK signal is in the form of B of t into AC cos omega ct. But once it is allowed to the channel, in the channel due to some noise, let the introduced phase deviation be theta. That is the first step. What is the first step? We have assumed the received BPSK signal form as B of t into AC cos omega ct plus theta. What is theta? Theta is the introduced phase deviation. Theta is the introduced phase deviation due to the noise present in the channel. Due to the noise present in the channel. Okay. And what is square law device? Now this already I told you that this BPSK signal is applied to the square law device to generate the coherent carrier. To generate the coherent carrier. And this is also applied to the multiplier, that is synchronous demodulator. Okay. So what this square law device will do? Already I told you that for the generation of coherent carrier, we don't consider the amplitude part. And this is also the PSK, because in PSK the amplitude of the modulated signal is constant. It is same as that of synchronous carrier, but the difference lies in the phase. So what the square law device will do? Square law device does not consider the amplitude variation. So you will get, so B of t into AC we don't consider. So B of t is plus or minus 1. So plus or minus AC we don't consider. Only the frequency and phase portion is assumed. What is the frequency and phase? Cos omega ct plus theta, that portion we will consider, but that B of t into AC we don't consider, because this is binary PSK detection technique. So now while generating the synchronous carrier, don't consider the amplitude variation. Now what is the output of square law device? Square law squares the corresponding term, corresponding magnitude. So cos square into omega ct plus theta you will get, because we did not consider B of t into AC. That is amplitude variation. Don't consider the amplitude term. Okay, therefore square law device output will be cos square omega ct plus theta. It will be 1 plus cos 2 omega ct plus theta divided by 2. Because I think you know that this is based on the trigonometric expression that cos square theta can be represented as, or cos square x, you can represent it as 1 plus cos 2x divided by 2. So based on the trigonometric expression, you can get the second equation. What is the second equation? Output of square law. That is cos square omega ct plus theta. You can write it as 1 plus cos 2 omega ct plus theta divided by 2. Now what? Let us go through the band pass filter. The output of square law device is applied to the band pass filter and then to the frequency divider, so that you can generate the coherent detection, carrier. What this? Let us go through the band pass filter. Third point, please observe. Band pass filter does not allow the DC component. What is the DC component here? Magnitude term, that is 1 by 2. And also the magnitude term for cos 2 omega ct plus theta. The magnitude is 1 by 2. So the magnitude term will not be considered by the band pass filter. Here band pass filter also eliminates the the DC component and magnitude term. So what can be the output of band pass filter then? Band pass filter allows cos 2 omega Ct plus theta, because band pass filter should allow the higher frequency component. Okay, it don't allow the DC component and the magnitude term. So band pass filter input is 1 plus cos 2 omega Ct plus theta divided by 2. Once that is applied to the band pass filter did not allow the DC component and magnitude term. So you will get the output as cos 2 omega Ct plus theta, cos 2 of omega Ct plus theta. Now what is the that is applied to the frequency divider. Please observe the fourth point. Frequency divider, it means that divided by 2. Already I told you that in binary PSK, the frequency divider is divided by 2. But in MRA PSK, what is the frequency divider? How much frequency you will divide? Divided by M. This frequency divider by 2 generates the synchronous carrier. Let that synchronous carrier be C suffix S of t, which is because the frequency divider input is cos 2 omega Ct plus theta. Okay, if it is divided by 2, if the frequency is divided by 2, you will get the carrier as, once you divide the angular part with 2, you will get only omega Ct plus theta as the angle. So that is cos omega Ct plus theta. Okay, so you may get a doubt. Why to square the angular part and why to divide it? Can't you directly consider as cos omega Ct plus theta? Actually, if you make use of, our researchers observed that by making use of square law device, band pass filter and frequency divider, you can stabilize the carrier. Okay, you can stabilize the carrier. That's why these three sections are used in BPSK detection technique. Okay, these three sections are used for generation of stabilized coherent carrier or stabilized synchronous carrier. Okay, C suffix S of t is cos omega Ct plus theta. So finally you got the carrier and one of other input is received BPSK signal. Both are applied to the multiplier. Let us see the multiplier output. So received BPSK signal and synchronous carrier that you generated by using three sections. What are the three sections? Square law device, next band pass filter, and then what is the last one? Frequency divider. Here frequency divider by 2. So synchronous carrier, both are applied to the demodulator. So the demodulator consists of multiplier. Multiplier, I think you know that it simply takes the product. Let us take the product. So what is it is yes, BPSK signal into synchronous carrier. Please observe the multiplier output. BPSK signal into synchronous carrier. What is BPSK signal? BPSK signal is B of t into AC cos omega Ct plus introduced phase deviation, that is theta. What is the expression for synchronous carrier? Cos omega Ct into theta. If you multiply those two, you will get the output as B of t into AC into cos square omega Ct plus theta. You will get cos square. Now please replace the amplitude of carrier in terms of power dissipated per symbol as root 2 ps. So you will get B of t into root 2 ps into same cos square omega Ct plus theta. Please once again replace cos square omega Ct plus theta as 1 plus cos 2 omega Ct plus theta divided by 2. Now here inside the root you will have 2. But in the denominator root 2 actually you have in the numerator, at denominator you have 2. So if you take that 2 from the denominator inside the root, you will get it as root ps by 2. Okay, because 2 you can write it as root 2 into root 2. So one of the root 2 gets cancelled and you will get root ps by 2. And so what is the output? B of t into root ps by 2 into 1 plus cos 2 omega Ct plus theta. It is the multiplier output. Please remember this multiplier output. It is the product of BPSK signal and synchronous carrier. So now this multiplier output is fed to the low pass filter and bit synchronizer to achieve the timing synchronization. Okay, multiplier output is simultaneously fed to bit synchronizer and low pass filter. Okay, let us see the integrated output. So I think you know that what this integrator will do. Integrator will, this low pass filter will perform the integration. Now here already I told you that bit synchronizer generates the series of pulse train. Let us consider one pulse having the bit duration as t suffix b and it starts from 0. See, please observe the pulse. It starts from 0 and ends up to tb. Now already I think you can observe two switches. S1 is closed at t is equal to 0. So when you will close S1, so you will close S1 at t is equal to 0. That is, at the starting of the pulse, you will close the switch S1. Once this S1 switch is closed, then the integrated data, that is the data reduced to 0. Integrated data is reduced to 0. And next, when integrator will you will perform, integration is performed during the duration from 0 to TB. At that time, S1 and S2 switches both you will make it as open. Once you open the two switches, then directly the integration will be performed. That integration will perform whenever the time interval exists between 0 to TB. Okay, and when S2 will be closed, whenever you close the S2, you will close S2 at t is equal to TB. Exactly at the bit duration TB, we will close the switch. Once switch is closed, the integrated data will be fed to the decision device. Okay, so when S1 will be closed, when S1 is closed at t is equal to 0, the integrated data is reduced to 0. And when S1 and S2 both are open, when you will make it as open, when t lies in between 0 to TB, okay, both the switches will make open. Once both are open, integration will perform by the low pass filter. When S2 is closed, when you close the S2 at t is equal to TB, then the integrated data is fed to the decision device. So after completion of bit duration, the integrated data will be fed to the decision device. So within the time bit duration, integrator will perform. So before starting of the pulse, earlier data will be reduced. Earlier integrated data will be reduced to 0. So same procedure will occur for all the pulses. Okay. Now for example, let us see the integrated output at some kth interval. Okay, let us observe at kth interval, that is at t is equal to some ktb. So what is the integrator output? Let the integrator output be S0 of ktb, because you are observing the output at ktb interval, at kth bit interval, that is k into tb. So kth bit interval is represented as k into tb. Nth bit interval is represented as n into tb. Now let us observe the integrated output. So in order to calculate the integrated output, the integration limits will be, you are observing at kth term. So the lower limit will be k minus 1 TB and upper limit will be ktb. So the integration will be performed for the low pass filter input. What is the low pass filter input? Multiplier output. Already we calculated multiplier output in the last slide as b of t into root ps by 2 into 1 plus cos 2 omega ct plus theta into dt. Okay. So integration limits will be, lower limit will be k minus 1 TB and upper limit is k into TB. Now always remember that the integration of sine or cosine term over the complete duration is 0. Okay. So integration of either the sinusoidal term or cosine term for a particular cycle is, so that's why the integration of cos 2 omega ct plus theta is 0. So you need to get integration only for this b of t into root ps by 2. That's all. Okay. So if you take the integration, you will get b of t into ktb because limits will change. B of t, because at t is equal to ktb you are calculating. So b of ktb into root ps by 2 into the time limit t, having the lower limits as k minus 1 tb and upper limit as ktb. So you will get it as b of ktb into root ps by 2 into tb. Okay. So it is equals to b of ktb into tb into root ps by 2. See, after integration, you will get the output as b of t into ktb into tb into root ps by 2. Because ktb minus ktb plus tb you will get, ktb and ktb gets cancelled. So you will get only tb at the output. So now this low pass filter output is fed to the decision device. So what is the low pass filter output? B of ktb into tb into root ps by 2. This is applied to the decision device. So what this, so therefore low pass filter output is B of ktb into tb into root ps by 2. This is fed to the decision device. What this decision device will do? It will compare the low pass filter output with the reference. It will compare the low pass filter output, that is S0 into ktb, with the reference voltage, that is V reference. And we already know that when low pass filter output, that is S0 into ktb, if it is greater than V reference, the decision device output is 1. If the low pass filter output, that is S0 into ktb, is less than or equal to V reference, the data is, the decision device generates the output as 0. Thereby you can attain the digital signal by comparing the low pass filter output with the reference voltage. So now the coherent detector estimates the output signal with less probability of error. Okay, but here the implementation is difficult, but you will get the effective result. That is the advantage of the general BPSK. But we have only one drawback, that is the implementation is somewhat difficult compared to BASK. Which implementation? Not the transmitter section. So the coherent detection implementation is difficult, but this generates very high SNR with less probability of error. So these are the advantages and disadvantages of BPSK. See, what are the advantages? Here also bandwidth is same as that of BASK. How much bandwidth? 2 FB. So in terms of bandwidth, it is high, efficient in terms of, highly efficient in terms of bandwidth. And second point is, here we don't have any amplitude variations because the modulated signal consists of only the phase variation, no amplitude variations. So that's why, so it has high noise immunity. So it is less susceptible to noise compared to BASK and high noise immunity. And third advantage is, it's already I told you, Euclidean distance is twice to that of BASK. So the isolation will increase. Once the isolation between the 2 points increases, this leads to decrease in the probability of error because Euclidean distance is inversely proportional to probability of error. So as the Euclidean distance becomes twice, the probability of error almost reduces like very much compared to BASK. We can't say exactly half, but it reduces a lot. So probability of error is less in the case of BPSK because of its high Euclidean distance. Next point is, BPSK system offers high power efficiency. Already we observed the generation technique and coherent detection. It generates like high signal efficiency. That's why in numerator section is high and probability of error is low, that is denominator is low. So our SNR becomes very high. So SNR for BPSK signal is very high. And what are the drawbacks? Let us observe the drawbacks. Here in the case of BPSK signal, the only drawback is the design of coherent detection is complex over BASK and PFSK. But other than that complexity in the receiver section, everything we have lot of advantages over BASK and BFSK. Okay, so over BASK you can evaluate it now, but BFSK we can, after discussion you can compare. And one more drawback is that here if you observe the output of BPSK signal, so it will have the amplitude change. If you carefully observe the waveform, you will have amplitude change between the symbols due to phase discontinuity. So when for the data bit 1, you will have same phase as carrier. For example, if the next bit is 0, suddenly its a phase changes. The phase will be 180 degree. So suddenly, actually it should go to higher magnitude, but suddenly there is a rapid change to like lower magnitude because the phase should be 180. So during these transitions, during this phase discontinuities, our amplitude rapidly changes. That is near the phase discontinuities, there is rapid amplitude changes between the data bits. This leads to ambiguity in the output signal. So the design is difficult, and second drawback is due to this phase discontinuities, the amplitude suddenly changes. Due to the phase difference, the amplitude suddenly changes at the phase discontinuities. So wherever you have phase transitions from like actual value to 180 degrees phase shift, will have amplitude transition will also be there. That amplitude change is rapid. So that's why we'll have ambiguity in the output signal. Okay, these are the advantages and disadvantages of BPSK, and these are all the applications. Nowhere it is everywhere used BPSK system, but we have little complexity in the coherent detection. But other than that, it has so many advantages. Its SNR is very good, less probability of error, and next bandwidth efficient system. Okay. So what are the applications in optical communications, like LAN, wireless LAN, next biometric systems, even this RFID tags, next local oscillator. So where you can use this local oscillator, everywhere you can use this local oscillator, because using this BPSK you can generate the synchronous carrier, which is stabilized one, by using 3 sections, namely square law device, band pass filter, and frequency divider by 2. Similarly, add and delay demodulators, wavelength division multiplexing, we can make use of BPSK, Bluetooth communications. So in all these applications, BPSK is generally used. So we have so many advantages of BPSK over BASK technique. So I will submit this in the WhatsApp group. You can go through that. With this, BPSK is completed. In the next class, we can discuss the differential PSK, which is a non-coherent version of BPSK. After that, we can continue differential encoded PSK. Okay, I took the attendance. Now you can leave the class. So any doubts in the today's session? If no doubts, you can leave the class. Otherwise, I will submit the material today. You can go through that, and if you have any doubts, you can ask in the next class also. No problem. Because without any material, how can you be able to ask the questions? Okay. Okay, you can leave the class.